Hello everyone, welcome to this physical sciences lesson all about the topic of electromagnetism. Today we're going to explore the effect that a current has and trying to see if it has a magnetic effect. Electromagnetism, two aspects of this topic, and that's exactly what we're going to do. So let's go and have a look at this in a little bit of an overview. Electromagnetism, we recognize, has two components. It's the idea of an electric current, which we're going to spend some time on, and we're also going to look how that links to magnetism and how those two interact to form this idea of electromagnetism. But to get started, I wanted to ask a question, and I want you to think about this very carefully. Maybe you've had somebody doing some DIY work at home, or you've noticed somebody doing some building. They're installing kitchen cupboards. And we know that inside the walls of a house, there are these conduit pipes that carry your electric current. So how does the DIY person know where to drill a hole? Look at the question. How does the handyman know where to drill a hole in the wall that doesn't hit an electrical cable, that's hidden in the wall? Can you imagine if that happened? Just pushing the drill bit into the wall, and suddenly you hit the electrical cables. If those cables are on, you're going to get an awfully nasty surprise. A shocking experience, I would say. Now, how do you know that that handyman knows exactly where to drill so he doesn't hit the cable? I want you to think about that. And you know what? The lessons we're going to learn, the content we're going to learn about today, gives us a way to be able to identify so that we don't ever make that mistake of drilling into a wall and hitting an electrical cable. But we'll have a bit more to say about that in a few minutes. Let's start by asking this question. The key terminology that you're going to come across. Remind yourself about what you understand about the word current. It's the flow of charge. And what about conventional current? Well, that tells us the direction of the current. And a field, well, the field is all about an area in space. An area in space where something might have a force on it. And so in this context, we're talking about a magnetic field. These are ideas that we're going to be talking about in a little bit more detail. So let's jump straight into it, and let's focus for the moment on current. Think about all the formula and think about the units as we revise these ideas as we look at this topic of electromagnetism. So we go to current and we recognize that current is the rate of flow of charge. It's a movement of charge. The symbol for current is I, and the equation that we use to calculate current is I is equal to the charge Q divided by the time. So that's why we say it's the rate of flow of charge. And of course, the unit for current is, the symbol is A, and the unit is an ampere. We don't say amps, we say A for the current. Now, what are the conditions for a current to exist in a circuit? Well, very simply, we need to have a source of energy. We need to have some sort of conducting device, usually conducting wires, and even a light bulb has conducting wires in it. That gives evidence that there is a current, and we recognize that we need that circuit to be a closed circuit. So tick the points here. We need a source of energy, we need some conductors, we need a closed circuit. And I've put together a simulation that we're going to have a look at right now. So here's my circuit. At the moment you see there's no evidence of current passing through the light bulb because it's an open circuit. Yes, we have a supply of energy, a battery that has stored chemical potential energy that's going to be converted into electrical energy. But at the moment, we've got conducting wires, but it's an open circuit. Let's have a look at what happens when we close the circuit. And as you see, no surprise, the light bulb starts to glow. And those yellow lines that are indicated there are indicating that there's an energy transfer, electrical energy converted into heat and light. So that's one of the effects of current. Current passing through a very thin wire is able to cause a heating effect, heats up that resistance wire that even produces light in the case of the light bulb. But if we were to take a look at what's happening on a micro level, we'd recognize there are charges moving. And this is where it becomes a little bit more controversial, because some people like to follow the movement of electrons. And other people say, no, let's think about what would happen if we had a positive charge. And so we have this idea that the direction of current is given by a convention. It's a rule, like we have a rule of driving on the left-hand side of the road in this country. We have a rule for saying the direction of current is the direction in which a positive charge would be likely to move. Let's have a look at it. I'm going to turn on the direction of current, and I'm going to say I want conventional current. Now notice this conventional current is moving from the positive end of the cell, that is the orange end, and it's moving towards the negative end around the battery. Those little red arrows are telling us exactly in which direction the current is moving. So that is conventional current. Just notice that we could change it to electron flow, and now you'll see it's in the opposite direction. And this happens in all situations. We're not going to take the direction of the movement of electrons. We're going to be confined to taking conventional current. Remember, when the switch is open, there is no current passing through the circuit. So there we've been able to see the idea of direction. And it's a very important thing. In this section, we're always going to be saying, what's the direction of the current in a conductor? And please make sure that you don't get confused. We always take the direction of the current as being the conventional current. And so have a look at how we've summarized it. We say conventional current is the direction that a positive charge would move within a circuit. We recognize that the direction of the current is from the positive terminal to the negative terminal. And so we indicate that on the diagram. We say that that was the positive terminal, that's the negative terminal. And as you can see, the red arrows indicate the direction. And so if I just change my pen, because it's not going to show up there, we'd recognize that's the direction of the current passing through that particular circuit. Now, it's all very well doing it in that scenario, but let's take a little bit of a focused situation here, and let's show the direction of the current. Now, there are different ways of showing the direction of current depending on your viewpoint. At the moment, we're going to take a look at a conductor, a piece of copper wire. And we've laid out the piece of copper wire over here. Recognize that we've got the positive terminal over here, and the negative terminal over here. The copper wire is indicating that it's connected to a power supply, and we're recognizing that the direction of current is from the positive to the negative. So we're looking at the top of the conducting wire, and we're looking, if you like, at a longitudinal section. We recognize that the length of the current, the arrow indicates the direction of the current. Of course, if the terminals were the other way around, from positive to negative, we would show the arrow in the opposite direction. And so that's a way of indicating current. But guys, there's a little bit of a problem. We don't always look at the length of a conducting wire. Sometimes we want to change our viewpoint. Maybe we want to look at the end of the conducting wire. And this creates a little bit of a dilemma for us. How are we going to show the direction of the current if we're not looking on a sideways view but a front-on view. Let me explain by showing you the diagram. And so if we have to look at these two situations here, this is the positive terminal, and we recognize the direction of the current is from positive to negative. So if I put my eye over here, I'm going to say the current is going in to that conducting wire. It's going into the piece of wire, and it's moving away from me. Now, by definition, we have a symbol to show when something is moving away. And it reminds us of shooting an arrow or throwing a dart. If you throw a dart, you'll see the back of the dart, and we represent it as a cross, the crosshairs of the dart. On the other hand, if we had to put our eye over here, then you would see the arrow coming towards you, and we would put a dot coming in that direction because it's the tip of the arrow. So we're using dots and crosses to show the direction of the current, not just an arrow. And this is particularly important. Remember, we can do this in many different situations. If we had to turn around the piece of wire and look from the other direction, the dot and cross would change direction. Well, that's summarized for us, just an introduction to the ideas of current. Don't go away. We'll be back to investigate a little bit more about magnets and the magnetic field. Thank you. Welcome back, everyone. Remember that we've just been discussing and revising some ideas about current, electric current. And particularly, we've looked at the direction of an electric current. And we said we're always going to give the direction as conventional current. We're going to use arrows, crosses, and dots to represent the direction of an electric current. Now, we're going to find that we can do exactly the same with a magnetic field. But let's explore a little bit more about what I mean by the word magnetic field. So that's where we're talking about. We're talking about magnetism, and we're going to talk about the magnetic field and what a compass is, and we've got some key words to look at. So the first thing we're going to mention is the idea of a field. Now, guys, remember, magnetism is one of those non-contact forces. You can have two magnets separated a distance, and they'll experience a force of attraction or repulsion. The other non-contact force that we talk about is gravity. The third one we talk about is the electrostatic force between two charges. Now, the field idea is a region in space. A region in space where if you insert something with a special property, it will experience a force. And the direction of the field is the direction of the force on that object. So when we talk about a magnetic field, we're saying that at the center of that magnetic field, there's a magnet, and in the region in space, three-dimensional region in space, anything that has a magnetic property is going to experience a force. The direction of the field is given as the direction of the force acting on that piece of magnetic material. And more specifically, we use a compass, which is a free-floating magnet, to give us the direction. But we'll have more to say about that just now. So magnetic materials, and I've mentioned this word, are just things that respond to a magnet. So they experience a force when you put them in the space of they are magnetic because they experience a force close to a magnet. And that's quite an interesting idea. Now, a magnet is a special material where the elements, the atoms inside the magnet, have a particular arrangement of electrons. And we say that they have what we call magnetic domains. Due to the movement of electrons within the atom itself, they form a particular type of magnetic field, a very small localized magnetic field, but they all contribute together. They all line up like soldiers and they form a straight line. In other materials, yes, there's a magnetic field at a micro level, but they're randomly arranged. So in a magnet, they're all lined, they're all very powerfully aligned. So we add up all that sum of that magnetic force, and we find it increases. So that's the idea of a magnet. And lastly, a compass is just a free-moving magnet. So it's sitting on a needle, and it aligns. It can move depending on which force it's experienced. If there's no force, it would just rest, and it could even just spin around without any particular force. But if you put a magnet near a compass needle, it will be attracted or repelled depending on what the pole of the magnet is. So let's have a careful look at this idea of the magnetic field. So we recognize that a magnetic field is a region in space. Remember, it's three-dimensional. Now, often we only draw a two-dimensional pattern, and it's usually drawn around a magnet, just like we could have drawn an electric field around a magnetic charge, an electric charge, we draw the magnetic field around a magnet. And we say within this region, magnetic materials will experience a force. Guys, this is very important. And I've got you to, I know I've repeated it a couple of times, but I want you to understand that it is not something we can see. This magnetic field is invisible. But when we put a magnetic material into that region, it will respond. So what magnetic materials do you know about? Well, probably the most common magnetic material that we've got, and you're aware of, is iron. An iron nail will easily be attracted by a magnet and will stick to a magnet. Steel will do the same. And if we want to see very small particles of iron, we call them iron filings. And this becomes a really interesting way to represent a magnetic field. So we can take a bar magnet, put a piece of paper on top of it, sprinkle some iron filings and tap the paper. You know what? All of the little iron filings start to align themselves to the magnetic field. And so that's the diagram that I've got here. If you zoom in on it, we don't know which is what end of the magnet, but we'd recognize one of the ends of this magnet would probably be a north pole, and the other end would be a south pole. Now, there's no way that I can know this, but what we know is that it's a pole because in that region, can you see that there's lots of iron filings sticking to that end? And we say that a pole is where the magnetic field is all pointing in the same direction, and it's very strong. So lots of iron filings are gathered in that area. Whereas if you look over here, the magnetic field isn't as strong. And if we look way out here, there's hardly any pattern that's happening. But we'd recognize that if we said that's the North Pole, that there's this loopy pattern that goes around a bar magnet, and it spreads out, almost going from the poles spreading out in that direction. And so there are these field lines that we use to indicate the direction of magnetic field. Of course, what is the direction and how can we tell? Well, we've got to use a magnet. I've got a little simulation I want you to show you that I think will be quite useful. But before we do that, let's just have a recap. Magnetic field is kind of interesting because it doesn't really have too many symbols, but magnetic field strength has given a symbol B, and it's measured in the units of Tesla. Now, Tesla is famous because of the electric cars, but really, Elon Musk depends on this idea of electromagnetism. Tesla isn't just about cars, but is about a very famous physicist whose name was Tesla, and he did lots of research about and inventions about electricity and conveying electricity. Some people think he was one of the most brilliant genius physicists of all time. Of course, he had competition. Michael Faraday was one of his competitors, and so was Benjamin Franklin. And so within the body of science and physics knowledge, Tesla has kind of not been a mainstream actor. But he is honored today with the symbol for magnetic field strength. So remember, where we have lots of field lines, lots of strong attraction to magnetic field, that's magnetic field strength, given the symbol B. Right. Now, the direction is the direction that a force is indicated on a free-moving North Pole. And we say that's really the compass needle. So the direction of the compass needle point will give us the direction of the magnetic field, and we can see that exactly here. Isn't that an amazing little simulation? So from the North Pole, look, the compass needle, the red side is the north end, and it's being attracted to the south end. These lines here are known as the field lines. And if you notice, all of the ones at the North Pole are pointing away from the north towards the south. Let's just stop the simulation and have a look at it in a little bit more detail, where I can annotate on it as well. So in this area here, take a look. All these field lines, these lines are pointing in the same direction, away from the North Pole. And they're looping around towards the South Pole. They're coming in at the south, and they're going away at the north, and they're forming this sort of butterfly winged pattern. On the inside of the compass, of the magnet, they would be going from south to north. So there would be field lines on the inside, and they're moving from south to north. On the outside, they're moving away from the north and towards the south. So on this side, look at this loop. Over here, it's moving away, and it's moving towards the south. Now, that's one particular view, and it's an easy way to represent it, but it's not the only way to represent the magnetic field and the direction of the magnetic field. Can you think of another way that we could do it? Well, you got it. We're going to use dots and crosses, just like we did for current. Because if we were to take a different view, not the top view, but the side-on view. So I've drawn a little square there to indicate the direction that I'm looking at the North Pole. And so what do you think I should do inside the box? Well, the arrows are coming out. So I'm going to put little dots over there. Okay? So those little dots represent the magnetic field that is coming out of the compass at that point. And what about on the outside? Well, look, here is where they loop away. They're going away. They're moving in that direction. So in this side, if my eye was over here, then I'm going to see them coming towards me and going away from me on the outside. So I'm going to put dots, crosses around here. Now, that's at the North Pole. What about at the South Pole? I'm going to see that on this side over here, they're going in. So I'm going to put crosses over here to show they're going in. And what about them on the outside over here? What's my eye going to see? My eye is going to see them coming towards me. So I'm going to put little dots on the outside. And so my magnetic field now is represented by dots and crosses. Isn't that a great way to represent the direction of the magnetic field? Welcome back. We're busy examining the idea of electromagnetism, and I'm sure you remember that we've spoken about electric current and magnetism. Now we're going to put the two together and start to consider and explore how they influence each other. So let's go and look at how we're going to do this. So the idea of electromagnetism is an important one because it deals with the idea that there's an electrical component as well as a magnetic component that we've got to look at. So the first part, electro, that deals with current, and this part, magnetism, deals with magnets and magnetic fields. And we are going to see how these interact. And we're going to try and see if we can detect a magnetic field somewhere related to a current moving through a conductor. Now, think about it this way. How would you detect a magnetic field? Well, we've done it already. We've recognized that when you have a magnet, you can use iron filings, or you can use a compass. And so with that in mind, let's have a look at the type of experiment that physicists did. It was almost by accident, to find that when there was a current passing through a conductor, there is, in fact, a magnetic field associated with it. And we're going to explore and ask some questions about that to unwrap what this mysterious thing of electromagnetism is all about. So, to find it, we're going to use a magnetic material. In this case, why not some iron filings? It worked for a magnet, so why wouldn't it work around a compass? Around a current conductor. And of course, we could also use a compass. Now, we can do this in different ways. It's interesting to note that when we do the experiment, the iron filings give us the pattern. And just like they gave us a pattern around a bar magnet, they don't tell us the direction. We're going to need to use a compass to see what the direction is. And remember, if we've got a magnetic field, a compass needle will point, the north side of that compass needle will point in the direction away from the North Pole. It will be repelled. It won't follow the normal direction of the geographical thing that we use a compass for, finding north on the surface of the Earth. It's not going to do that. It's going to tell us the direction of the magnetic field at a point close to that current carrying conductor. So let's have a look at it. And here's the experiment. We've got a little circuit here, and I want to just illustrate and highlight some things. There we've got a power supply. It's a collection of cells that are connected in series, and we recognize that gives us the one thing that we're going to need for current to pass through a circuit. The second thing is we recognize on this diagram there are conducting wires. So this is a wire and this is a resistor, but we've got a closed circuit. And so we recognize there must be a current that is going to pass through these wires. If we wanted to ask what's the direction of the current, remember the long end of the symbol is giving us the positive end of the battery. So we'd recognize conventional current is from positive to negative. And so the current direction here is up into this piece of paper, and that piece of paper or card is lying perpendicularly to the direction of the current. So the current is going up, the wire is going up, and at this angle here, 90 degrees to it, we've got the piece of cardboard, and on that piece of cardboard we sprinkled some iron filings. And what you notice here is that there's a pattern. Notice that the pattern is kind of a circular pattern. Even these ones out here, it's kind of a circular pattern. And the further we go out, the less ordered we get. Here they're a bit confused. They're not particularly aware of what the pattern is. So strange, not like the butterfly effect that we got around the bar magnet, a different field pattern, a very different field pattern. Have a look at the diagram a little bit more, and you'll see that here's the compass needle, and that red arrow is pointing to the north. So if we had these compass needles, we'd recognize they would be pointing in that direction all the way around that circular loop. So it's quite important to recognize that the pattern, which is an unusual pattern, is given by the magnetic field, by the magnetic material, the iron filings. Compass needles can do it as well. When I've done this, I found that sometimes the compasses interact with each other. And so it's much easier to do it like this. We're going to do a little bit of exploration with this situation once we've got the idea. Notice, just made a note of it, that the pattern is given by the iron filings, the direction by the compass needle. Now, are you ready to investigate a little bit more and ask some questions about what affects this pattern around the current carrying conductor? Well, one of the things that we're going to do is to recognize that there is in fact a rule that will help us determine the direction of the magnetic field. And in this rule, known as the right-hand rule, we use the thumb and the fingers of the right hand to give the direction of the magnetic field around a straight conductor. The thumb tells us the direction of the current, and the fingers point in the direction of the magnetic field. So make sure that you've got your right hand ready. Don't use your left hand. Use your right hand. I'm left-handed, so it's a little easier, but I put my left hand behind my back, and I'm recognizing I'm only going to use my right hand. The thumb that I'm pointing out in front of you, that's coming towards you now, directing upwards, would show the direction of the current. The fingers will show the direction of the magnetic field. And the thing about the fingers is that they curl, so they can give us the direction in a circular motion. So please remember, get your right hand ready, and even if you've got to stand up and get closer to the screen, get ready to use your right hand as we investigate the direction of the magnetic field around a current carrying conductor. So hopefully we've got it here, and that was the same diagram. I'm now going to go to the simulation where we can do some changes of things. So the first thing that I want you to notice is that on the simulation, we've got the option of indicating the direction of the magnetic field. And we recognize that it's in that circular motion. We recognize the circular pattern on this side. Let's see if we can use the right-hand rule to show that. So what I want you to do is to recognize that the current direction was up, and recognize that the curl of the fingers are going in on this side and they're coming out on that side. So if you look at that, it's going in on this side and it's coming out. So in a circular way, it's representing the magnetic field. And remember, that magnetic field isn't just at one point. It's all the way around where the conductor is. Wherever the conductor is, we recognize we can use the right hand rule to show us the direction of the magnetic field. Now, one of the things this animation allows me to do is to increase the current. And if I increase the current, look what happens over here. The magnetic field pattern increases and it becomes more defined. And so we can see that very clearly. It's not making any difference to the direction over there. If I show my right-hand rule, you can indicate that very clearly. Now, what I want you to see is if we had to do it in the other direction, and sometimes people get confused in a test or whatever, and they say, I can't see the direction. Well, remember, you can just change your position. Change the piece of paper. We're saying the direction of the current is up over here, and it's coming out of the board on this side. And if I move it to this side, step out over here, recognize the current is up, it's going in on this side and coming out on that side. It's going in on that side, coming out on that side. Very important. I hope you can see what I'm building up to. If we have to show in and out, how do you think we could do that? We did it with current. We can do it with magnetic field as well. So let's not leave you in too much suspense, and let's recognize how we're going to show that direction. Well, you know what? I think we're going to just need to give you a break. Can you think about how to show that direction of the magnetic field? I did give you a bit of a hint. Perhaps you could have a little go at it. Write it down on a piece of paper. If the current is going up, in which direction would the magnetic field be? We'll be back straight after the break. Welcome back. I hope you've been able to work out what the direction of the magnetic field would be if we're looking at a straight current-carrying conductor. And if we're looking at it so that we can see the piece of wire, the conductor, lengthwise. Let's have a look and see how we're going to resolve this. And of course, the hint is that when we do this sort of thing, like we've got in this diagram, we can see that there's a circular magnetic field pattern. We recognize that the direction of the current, as we've shown it earlier, is upwards. So we can show that as a piece of an arrow pointing up. But now we're going to use the right-hand rule. And we recognize that if the thumb is pointing in the direction of the current, then the fingers are coming in which direction? Out of the board. And when something comes out of the board over here, then we can say on this side, out of the board, there are going to be little dots. So all the way along this board, there are going to be little dots. And if we use the right-hand rule again, and I just turn to this side, we recognize that the direction of the magnetic field is going to be into the board. And when we show into the board, we're going to use crosses. So you see, the cross dot notation can be used for either the direction of the magnetic field or the direction of the current. Just like we've shown earlier, it depends on where your eye is. So in this case, we're kind of looking at the piece of wire, the straight piece of wire, in a long form. We're looking from a side view. What happens if we change our point of view and we now look at an end-on view? For those of you that do life sciences, you can imagine that you're going to cut this piece of wire crosswise. We'd say it's a cross-sectional view. So think about your eye being in that position or in this position over here. We're going to either be looking at the top down, the current coming towards me, or from the bottom up, the current going away from me. And this is where it gets quite interesting. And so I want you to take time and follow me as we recognize, yes, this current does exist, and it exists depending on the amount of current that actually passes through the conductor. It can have different strengths. If it's a small current, smaller magnetic field, smaller effect on the iron filings. Bigger current, bigger effect. We can also recognize the direction of that field lines, so those magnetic fields will change with the direction of the electric current. So let's have a look now in terms of where our eye could be and showing a different position. So now if I've taken a cross section and my eye is looking from the bottom, and I'm saying in this case the current is going in which direction? The cross is going into this plane. It's going into the conductor. Now, what effect is that going to have? Well, it's going to produce a magnetic field around the conductor. And so we need to be able to use our right-hand rule to show that. So let's have a look here. If I take my right hand, be careful not to use your left hand. I'm going to use my thumb to show the direction, and I'm saying the thumb is going into the plane. In which direction is the curl of my fingers going? Well, I hope you can see that over here, the fingers are curling upwards, and over here, they're going sideways. And if I change my direction, and I'm moving to this side, they'd be going down. And over here, if I do it from the bottom, and I move my hand, you can see the curl of the fingers are going round in that direction. And so I've put little arrows to indicate the direction of the magnetic field. But in fact, what we can do is we can expand on the pattern that is given by the iron filings, and we can represent this magnetic field in terms of field lines. Now remember, field lines may not cross each other. So we start with those that are close to the conductor, and as they go further apart, we know the field weakens. Where the field is strong, the magnetic field lines need to be close together. So have a look at my diagram here. And as you can see, I've indicated the direction, confirm it, right-hand rule. The current is going in, the direction of the magnetic field is clockwise. Notice over here, these field lines are close together. They're not the same distance between the inner two and the second two. And they're certainly not the same distance, so they're not concentric. This is showing that as the distance away from the conductor increases, the effect of the magnetic field decreases. It's not as strong as it is close to the conductor. Very good. What about if we looked from the other side of that conducting wire? So instead of looking from the bottom now, we're looking from the top. The dot represents the current coming out of the plane, coming towards me. We need to recognize here that we're going to use the right-hand rule again. Don't get confused. Don't use your left hand. The dot is indicating, it's like the arrow coming towards you. You see it as a dot. You don't see the tail feathers. So the thumb now points towards you. It's coming out of the board. And in this case, you see the curl of the fingers is in the opposite direction. It's anti-clockwise. So at each point, I can show the curl of my fingers, and I can even move to this point and say, it's going around that way, and it's coming up this way. The thumb is still coming out towards you. I hope you can see that it's going to form that circular pattern that we saw originally. And we can represent that in drawings. When you do, please make sure that you use a compass to draw your field lines neatly. But they don't need to be the same distance apart. So just like we saw previously, in this representation, notice the direction here is anti-clockwise. It's coming out towards you. Some people make a point at learning those direction, clockwise, anti-clockwise. I don't bother. Just use your right-hand rule. Your right-hand rule really gives it, you've got enough to remember with definitions. It's better to learn that and to learn how to use the right-hand rule. So current coming out, it's in that direction. Notice again, here, this is a weaker magnetic field. And here, it's a strong magnetic field. So this field is not uniform. It's not the same strength everywhere. And so I want to just pick up on that point by having another look at this view, the longitudinal view, and recognize how we're going to represent the current around this. We've done it very quickly earlier on, but let's just do it in a little bit more detail. First thing, we're going to recognize that the direction of the current is conventional current. It's from the positive terminal to the negative terminal. We recognize too that there we can use the right-hand rule. The right-hand rule tells you, take your thumb, point it in the direction of the current. Now look what happens when I do that. The thumb is pointing in that direction, the same direction as you can see the current is. Now if I turn my fingers, in which direction are the fingers coming? They're coming out towards you. They're coming towards you. So at the top here, they're going to be coming out of the board. And so we would need to put over here a representation of something coming out. What will that be? A cross or a dot? You've got it. It's a little dot. So we're going to say there are the dots, and these dots are going to be close together because it's representing a strong magnetic field. But now have another look. If I have this direction of the current, what's happening below the below this conductor? Below the conductor, the fingers are no longer coming towards you. Which way are they going? They're going away from you. They're going into the plane of the board. And so we recognize we're going to show those as little crosses. And so we recognize here we've got a method of representing the direction of the magnetic field around the conductor. In more detail, I've put in further away from this current carrying conductor. And what I want you to see is I've deliberately put the crosses on this side close together. That's a strong magnetic field. Over here, they're further apart. They've decreased. And so they spread out. And that's representing a weak field. So even over here, there are fewer of them. Over here, the field would be weak, but close together, they'd be strong. So it's quite important for you to recognize that. The question is, what happens if we switch the terminals? If we switch the polarity of the battery? Well, here we go. Now we've got the positive end on this side, got the negative end on that side. What do you think we're going to do? Well, we do exactly the same as before. But notice what happens now. We put the thumb in the direction of the current. In this side, it's going in at the top, above, and it's coming out at the bottom. And so that's exactly what I've represented over here. And recognize again that when they are far apart from each other, those field lines are representing a weak magnetic field. This is weak, where this is stronger. Very good. Let's summarize our last few points over here. The summary that we're looking at is recognizing, first of all, that around every current-carrying conductor, there is a magnetic field. Guys, this doesn't matter how strong or weak the current is. If the current is very small, the magnetic effect will be very small. The magnetic field will be very small, but it's still there. If the current is very large, then the magnetic field will be much bigger. Recognize that the direction of the field is perpendicular to the current direction. And remember, we use the right-hand rule to find the current and field direction, and we use dots and crosses to represent when something goes, when it's a dot, it's coming out. When it's going in, then we use a cross. Guys, I hope you've enjoyed that introduction to looking at electromagnetism. So please don't forget it. Practice, draw diagrams, and we'll see you again pretty soon.